Okay, so I want you to think about some kind of electrical device. And this device can actually be anything. I mean, anything electrical. Computer, amplifier, whatever. So I'll just put device here. So any kind of electrical device is going to have a place where you connect it to power. So I'm going to put that over here, and I'm just going to draw these terminals like this. And these are just like connection points. I mean, it could be a plug, it could be something you screw wires to. We'll call this the input. And over here, we'll call this the output. So if you think hard enough about this, every electrical device has some kind of an input and some kind of an output. It could have more than one input or more than one output, but we're just going to consider devices with one input and one output. Some examples might be, I use the amplifier. So an amplifier, of course, makes things louder. This is the symbol for an amplifier. And you put in like electrical energy here, right? And then you get out electrical energy. What you do is you hook up a speaker, and that amplifier will drive the speaker. So the speaker is not part of the amplifier. The speaker is actually something you hook up. So your cell phone, right? Your cell phone actually has more than one input. I mean, it has a battery pack. There's a battery inside your cell phone. So that's an input. Whatever the battery connects to is an input. And but there are other inputs, like for instance, you talking to your cell phone microphone. That's actually energy going into the cell phone, so that's an input. And if you have a touch screen, that's an input. So any way you can put energy into a electrical system is the input, and any way you can get energy of some form out is an output. And so, like with the cell phone, you can have more than one input, more than one output. So typically in electrical drawings, we put inputs on the left and outputs on the right. So I'm showing that here. Now, on the input, that's where we're going to connect power. So if I wanted to, I could put a battery over here. So this is my VN, my power. And typically, we want the device to do something. So it has some kind of an output. I think the amplifier example I had was a good one, because the output there is a bigger electrical signal, and to the output of the amplifier, you hook up a speaker. Well, the thing you hook up to the output is called the load. So I might take a speaker and hook it up to an amplifier. So here's my speaker. Here's my amp. So this is called the load. Whatever you hook up to the output of the device is called the load. Your cell phone charger. So you got the cell phone charger, and maybe this part right here plugs into the wall outlet. You got 120 volts AC. That's like the input. And over here, you got the wire that you plug into your cell phone. So here's your cell phone, and you plug the wire in there so you can charge your cell phone. Well, this is a device. The input plugs into the wall outlet, so you got voltage going in, and then the thing you hook to the other end of the charger, your cell phone charger, is a cell phone. So your cell phone is the load. So the load is whatever you hook up to the output of the device. The load, what the load is depends on what you have, right? If it's an amplifier, your load is probably a speaker. If it's a cell phone charger, your load is probably a cell phone. So the load depends on what it is we're talking about. But one thing that every load has in common, Your cell phone has resistance. The speaker has resistance. Anything that we will hook to the output of this circuit, of this device, has resistance. So what I can do, instead of worrying about whether it's a speaker or a cell phone or whatever, since everything has resistance, we can just model any load as a resistor. So in other words, what I'm saying is, in this example device here, whatever this thing is, I probably got some kind of load or something that I have put to the output because this device is going to do something. We'll call that RL. That's the load. So up until today, all we've been doing in this class is just we got resistors. You learned a lot about what resistance is, and you know what voltage is and current. We talked about power, energy. We talked about a lot of stuff. But I want to talk about electrical devices. And we're going to bring it to the circuit level. But in order to bring it to the circuit level, we just kind of got to back up and look at a whole device. And that's kind of what this is right here. So imagine this is some kind of device, whatever you want. And what's inside of here is, well, it depends on the device. You know, pretty much every electrical device is going to have a resistor or resistors in it. There are other devices we haven't talked about, like capacitors and inductors, and there's transistors and diodes, and the list goes on and on and on and on. And as you take more classes, get more experience, you learn about other devices other than resistors that could exist in here. But for us right now, all we have talked about so far is resistors. So our device, whatever this thing is going to just consist, what's inside of it is going to be resistors. And right now, we don't know what's inside of it. But let's say we can peek inside of the case, maybe take the cover off and peek inside of it to see how those resistors were connected. And let's just say that those resistors, let me put the word device up like this. Let's just say that those resistors on the inside were connected up like this. So I just got, this is a really simple device. It's got two resistors in it. It's got one resistor like right here. And then it's got another resistor like right here. Okay, so let's give these some values. Let's say this is a 6 ohm resistor, and this is a 3 ohm resistor. And let's say that my voltage over here is 9 volts. So I got this device, it's hooked up to 9 volts. It's running whatever this load is, and what's inside of it is this right here. Now, what I want to do is I want to figure out how much resistance does this battery, let's say the battery could think. If it can see these how much resistance does it see? How much resistance does it see in the device? What does it think the resistance of this device is? So imagine the battery had an eyeball, so it's looking in there. And what it's looking at is the resistance. So how much resistance is this device composed of? Well, if I want to do that, before I can talk about the resistance that the battery sees, I got to take this part off because the load is not part of the device. If I go back to the example of your cell phone. So if I have a cell phone charger that plugs into the wall, and I hook it up to your cell phone, and I say, all right, looking in this way, this is your eyeball looking in that way, what's the resistance of the charger? If you leave your load hooked up, the cell phone, then you give me the resistance of the charger and the cell phone. That's not what I want. I don't want the load, I only want the resistance of this thing. So if I want to find the resistance looking in this way, what I got to do is take the load off, because it's a separate component than the device itself. So I got to take this off over here. And if I take the load off, I'm looking in this way, how much resistance would the battery see? How much would it see?
9 ohms.
It will see 9 ohms. It will see 9 ohms. If everybody see why, it will see 9 ohms. It's going to see 9 ohms because basically since I opened up the output over here, basically this is a series circuit. So the 9 ohms is called the input resistance, RN. And if you're taking notes, what you want to write down is this. The input resistance of a device, or circuit is the resistance from the point of view of the power source, of the voltage source. The input resistance of the device is the resistance from the point of view of the voltage source, or you want to say power source, you want to keep it general. Now, we've already talked about that input resistance. You call that, if it's a series circuit, we call this RT. It's like the total resistance. It's a series circuit, so 3 plus 6 is 9. RT for this circuit is 9 ohms. If I had a parallel circuit, we call it REQ. Remember what I said in parallel, instead of calling it the total resistance, I'm going to call it REQ, but it's the same thing. So in this classroom, this resistance from the point of view of the battery, that resistance, we've already talked about and used that resistance. We just gave it a different name. We call it either RT, if it was a series circuit, we call it REQ if it's a parallel circuit, but you'll never, ever, ever see that outside of a school situation or textbook. If you go to GE, if you go to Procter & Gamble, if you do in any other kind of industrial environment, and you go in and you're working on electrical stuff, you will never hear the engineers, or you will never hear them talk about the total resistance of a device or the equivalent resistance of a device. You will hear them talk about the input resistance of a device. So this is a more practical term, and these are more theoretical. This is like a textbook kind of a thing. So the input resistance of something is the same as the total resistance or equivalent resistance. That's the first thing you want to write down and be clear on. We'll pause for a minute and let you write that down. Now, here's the new thing. That's all old. I mean, the way I'm presenting it might seem new. I'm talking about devices now, but total resistance is old. We've talked about that all semester. Total resistance, no big deal. But here's the new thing. Just like there's a resistance from the point of view of the voltage source, the thing I took off over here, the load, if I put the load right here, if I had an eyeball and I'm looking this way into the circuit, the resistance from the point of view of the voltage source, well, that's called the total resistance, equivalent resistance, or the input resistance. But I can also look from the point of view of the load. In other words, if this thing had an eyeball and it's looking in that way, how much resistance does it see? Now, to answer that question, there's some things we got to do, and we'll get there in just a second. But I want to impress upon you that there's always, we've only done calculations in this class up until today. We've only done calculations from the point of view of the power source. That's all we've ever done. Now we're getting ready to change it up because I can really do a calculation on the circuit from the point of view of anything. And the anything I'm talking about is whatever the load is. So this right here sees a certain resistance looking into the device, and the load sees a certain resistance looking into the device. Now this is the output over here. This is the input. And if I call the resistance looking into the input resistance, guess what I call the resistance looking into the output? What do you think I call that?
Output resistor.
The output resistance. The output resistance is the resistance from the point of view of the load. Write that down. The output resistance is the resistance from the point of view of the load. Now there's another name I'm going to give it. I want you to write it down, and I'll explain it here in a few minutes. The output resistance is the resistance from the point of view of the load. But the output resistance has another name too. The output resistance is called RTH, and that stands for the Thevenin resistance. RTH is called the Thevenin resistance, and it's also the output resistance. So here's how this works. In a school situation like Cincinnati State, UC, Xavier, if you're in a school or college and you're reading the textbook, they're going to refer to the resistance from the point of view of the voltage source. They're going to refer to that as the total resistance or the equivalent resistance. When you go to work at GE or Procter & Gamble or wherever you're working when you get your degree, you'll never ever hear those terms. They'll call it the input resistance of the device. When you are in a school situation like here, UC, XU, and you're talking about the resistance from the point of view of the load, it's called the Thevenin resistance. And in the textbook or in a lab situation, they call it the Thevenin resistance. But when you get out of here and you go to Procter & Gamble, GE, or wherever you're working, you'll never ever hear that word Thevenin resistance. You will hear them talk about the output resistance of the device. So this is more of a theory thing right here. This and this. And when you get out and start using this stuff, it's always this or that. Now, this gets a little more involved in that because not only is there a Thevenin resistance, there's a whole Thevenin circuit. That's what I want to talk about tonight, the Thevenin circuit. What the heck is a Thevenin circuit? Well, Thevenin was a person, and he came up with what we're going to talk about tonight. What we're talking about tonight is called Thevenin's theorem. Thevenin's theorem. And Thevenin came up with this theorem that basically gave us the circuit, what the circuit looks like, not from the point of view of the voltage source, but he gave us a circuit, what the circuit looks like from the point of view of the load. And you might wonder to yourself, well, why the heck do we need that? What's so good about it? Well, you'll see. It turns out to be second to Ohm's law. Second to Ohm's law and Watt's law, to me, the most important thing you'll ever talk about this semester is going to be this circuit right here. It's big. So, what is the Thevenin circuit? Well, it's called the Thevenin equivalent circuit. The Thevenin equivalence, what does that mean? Well, if I have something equivalent, that means that I can't tell the difference between the two. And I'll explain the details of that in a few minutes. We're getting deeper into this. So this turns out to be really important. So there's a whole circuit that this thing sees, and it's not necessarily this circuit right here. Matter of fact, the only way to see the circuit that the load sees is to go through certain steps. Now, I'm going to share a document with you. I don't know if you had a chance to print this off or not, because I put them up today, and I probably didn't put it up in enough time for you to print it out. So it's on Blackboard. If you didn't print it out, it's okay because it's there. You can just take notes, and you can go to print it out later. But take a look at this. Now remember, you can zoom in on this. So zoom in on this, and if you zoom in on this, you might notice something different about this topic sheet. This topic sheet has a lot of white space on it. You've never seen a topic sheet like this from me before. So much white space. Why the white space? Well, if you were face to face with me, and we're actually meeting, having this discussion, then what I would have you do is write some things down in that white space. And what you're writing down are steps to this Thevenin thing I'm talking about. And you would show a circuit for each step of the list that I'm going to give you here in just a second. But since we don't have the luxury of meeting yet face to face, and by the way, I don't know if you guys know this or not, but Xavier University, Cincinnati State University, and Cincinnati State University, Xavier University, University of Cincinnati, and Cincinnati State they got together, had a discussion, and they decided that they're going to go back to face-to-face classes, not in the summer, but in the fall. So this coming fall, we'll be back meeting face-to-face. At least the agreement between those three colleges and universities, we decided to go back, or they decided to go back in fall. We'll be back face-to-face. So Let's take a look at this first theorem there. You see that? It says Thevenin's theorem. Take a second and read the theorem to yourself, and then I want to read it to you. Right, now, so you had a second to read Feminist Theorem, and I want to read it to you now. And what I want to do after I read it, I want to dissect it. I want to make sure you understand every single word in this theorem. And then what we're going to do is show an example of it, because I don't believe just understanding the words, you can understand the theorem. You have to see it and practice it. That's what we're going to do tonight. So here's what it says. Feminist Theorem, any two-terminal linear bilateral DC network can be replaced by an equivalent circuit consisting of a voltage source and a series resistor. Feminist Theorem. Any two-terminal linear bilateral DC network can be replaced by an equivalent circuit consisting of a voltage source and a series resistor. Now, what the heck does all that mean? Let's dissect it. It says any two-terminal. Well, that's not too hard to understand. What do they mean by two terminals? Anybody? What does that mean? When you deal with electrical circuits, what do they mean, two terminals? What are they talking about?
Two inputs?
Yep. Every circuit has two terminals, right? One you call the what, and one you call the other. One you call the positive terminal, and the other is called the what? Negative terminal. So that's easy to understand. We have some kind of two-terminal. But then the next word, linear. What the heck does that mean? Linear. What does that mean to you when somebody talks about something being linear? You guys know what it means. What does linear mean?
And a line?
A line. One way to describe it in math is a line. If something is linear, when you graph it, it's a line. I want to say straight line, but a line by definition is straight. Another way of thinking about it is, if I have an equation, I can just look at it and determine if it's a linear equation because all the variables will be to the first power. And if I graph an equation with all the variables to the first power, I'll get a line. So why is this in here? Well, because any electrical quantity that we talk about, what do you mean by that? When we talk about voltage, we talk about current, we talked about power, we talked about energy, we talked about those quantities. They have to be linear quantities when described mathematically. And that's true of voltage, that's true of current, that's true of resistance, but it's not true of power. Because one way for me to write power is P equals I squared R. That's not linear. Another way for me to write power is P equals V squared over R. That's not linear. So since I can express that quantity of power in a way that's not linear, it has numbers raised to the second power, then it's not linear. If you graph it, it's not linear. You'll see that when you guys do the power lab. So this does not refer to power. And I'll explain what I mean by doesn't refer to power soon when we get some practice problems under our belt. So any two terminals, a plus and minus terminal. Linear means that whatever quantity I'm expressing in this circuit, voltage, current, resistance, it's got to be linear. If I graph that thing, it's got to be a straight line. It can't be a curve because then that's not a linear function. It's not a linear relationship. So Thevenin doesn't work with this. So power is out of here. We can't use power in this Thevenin circuit. Again, I got to explain the details of that. I just want you to understand what the words mean. So any two terminals, plus or minus terminal, linear, the quantity is to the first power. Bilateral. Bilateral. What does bi mean? When you put bi in front of it, what do you think of?
Two.
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 Bi means two. Now, let me switch off of this. I'm going to go back to a camera, to my camera. And I'm going to put this device on the board. Two of them. One you know, one you may not know. I don't know. So here's one that you know. That's a resistor. Here's one that you may or may not know. Does anybody know what this is?
Is that a diode?
Diode.
That's a diode. It's called a diode. Now, if you don't know, don't worry about it because you're not really supposed to know right now. You haven't got to that yet. You don't get to that until you take a course called electronics, if you take it at all. If you I don't know, some of you like electromechanicals, I don't know if you take that or not. I don't know. But don't worry about it if you don't know. But here's what you need to know about it. This is a bilateral device. The resistor, the diode, is not a bilateral device. What makes a resistor a bilateral device? Well, here's what does it. If I hook up a battery to the resistor, the current is going to flow this way through the resistor. What happens if I flip the battery over? What do you think is going to happen to the current?
It's going to change direction.
It's going to change direction and go that way. In other words, with the resistor, current can flow either way through a resistor. It's a bilateral device. You try the same thing with the diode. If you hook the diode up like this, then current will flow through the diode. But if you try to flip the battery over, current can't go the other way. Diodes are designed to only allow current. They act like a one-way valve for current. A diode is designed to let current run one way, but not the other way. So a diode is not a bilateral device. So bilateral means current can flow both ways through the device, or in this case, the circuit. So let's go back to the definition. Any two terminals, the plus and minus terminal, linear, any quantity in that circuit can be expressed only to the first power. Bilateral, current can go both ways through the circuit. Go from the input to the output, or from the output to the input. DC, everybody already knows that stands for direct current. Any two-terminal linear bilateral DC network can be replaced by an equivalent circuit consisting of a voltage source and a series resistor. In other words, guys, as long as it's a two-terminal linear bilateral DC network, I can replace it with this. I can replace it with this. A single voltage source and a single resistor. And this circuit is called the Thevenin equivalent circuit. I'm abbreviating here. I think I'm out of room here. The Thevenin equivalent circuit. And the resistance there is called the Thevenin resistance, RTH. Remember, that's the resistance looking into the output of the circuit. And the voltage source here is called the Thevenin voltage, VTH. So any linear two-terminal bilateral DC network can be replaced by that. I don't care how many resistors the circuit has. I don't care how many voltage sources the circuit has. You can give me the biggest circuit you can think of. You can give me a circuit that'll fill this room. You can give me a circuit with 1,000 resistors in it and 50 voltage sources, and as long as it's a linear bilateral DC network, guess what I can do? I can reduce it down to that. Now, which do you want to work with? Do you want to work with the really big, complicated circuit, or do you want to work with that? Most people want to work with this. So one reason it's important to understand the Thevenin circuit is because it's an equivalent circuit, which means it equals the big circuit, behaves like the big circuit, But there's another reason I think is more important. We'll get to that here shortly. So here's what we got to be able to do. Number one, I want you to understand what this circuit is. And number two, I want you to understand how to start with an original circuit and get to this circuit. Now, let's start with the first question. What is the Thevenin equivalent circuit? Here's what I want you to write down. The Thevenin equivalent circuit is the circuit from the point of view of the load. Write it down. The Thevenin equivalent circuit is the circuit from the point of view of the load. What the heck does that mean? Well, you see this load right here? If this load had an eyeball, it can look in there and it can think. It doesn't know anything about what's really in this box. What it really sees is this circuit. Every single circuit in the world, as long as it's a linear bilateral DC network, and most circuits are, from the point of view of the load, it sees only the Thevenin circuit. And so the Thevenin circuit is an equivalent circuit, but it's important to understand it's an equivalent circuit from the point of view of what? From the point of view of the load. Now, what I want to do next is I want to go through and give you a set of steps to properly Thevenize a circuit. And I'm using the word Thevenize as a verb. When I say Thevenize, I mean to start with the original circuit and turn it into the Thevenin equivalent circuit. And once we get good at doing that, then I can talk about the second reason for Thevenizing the circuit. The first one is what I said earlier. I'd rather work with this circuit than a more complicated circuit. If they're equivalent, I'd rather have a dollar bill than 100 pennies. They're equivalent, but the 100 pennies is too complicated, too much to deal with. I want to deal with something simpler. Well, the Thevenin equivalent circuit is always simpler. But there's another more important reason, the other information we can get from this that we'll talk about here tonight. So, if you wonder why on this topic sheet, well, why is there so much white space on this topic sheet? Well, here's where you would use this white space, because what I would do is have you write down these steps I'm about to give you. So I want you to do that now. You don't have to have this document. Just take out a piece of paper. And I'm going to give you some steps. Now, it's important that you do this exactly like I said, because here's what I'm going to do. I'm going to give you these steps, and then after I give you the steps, I'm going to give you the steps again, but this time I'm going to show you a circuit for each step. So this is going to take some time. I don't want you to rush through this. I'm going to go through this slowly, because what I want you to do is write it down, and if you don't get it the first time I say it, let's say you miss a step, it's okay. Because I'm going to go through it the second time. But the second time I go through it, we're actually going to do it on the original circuit. And what I want you to have is, for every step I give you, I want you to have an example circuit so that later on when you're doing this, you can look over and say, oh, okay, that's what I'm supposed to do. Okay? So take out, I'll give you a minute, take out a clean or blank sheet of paper, whatever you're taking notes on, your notebook, whatever you're doing. Get paper, you need some space for this. I want you to write down these steps. Write them down. Let's write them down as a list. Just write them down close together as a list. And then I'm going to give them to you again, and that's when you're going to need the paper, because you're going to say, okay, step one, here's what the circuit looks like for step one. And then step two, you're going to have to redraw that circuit again. Here's what it looks like for step two. You're going to draw the circuit like 4 or 5 times. So you need some paper for this. So go ahead and get yourself some paper. Get yourself... and the coloring pencils would be nice, color coded. Get whatever you need so that we can do this. And I'll give you a minute, and then we're going to go through the steps. Okay, so at the top of your paper, here's what you want to write. Here are the steps for properly Thevenizing a circuit. Here are the steps for properly Thevenizing a circuit. Step number 1. Don't worry about what it is, guys. Just write it down and I'll explain it. Step number 1, remove the load. Step number 1, remove the load. Write that down. Remove the load. Step number 2, name the terminals. Step 2, name the terminals. Step 3, calculate the open terminal voltage. Step 3, calculate the open terminal voltage. This will give you your value for VTH. That's step 3, calculate the open terminal voltage. This will give you your value for VTH. Now for step 4 is going to have an A and a B. So go ahead and write your number 4. And here's what I want you to write for number 4. For number 4, write, set the power source to 0. Just write that down. Set the power source to 0. Number 4, set the power source to 0. Set the power source to 0, number 4. And then right up under that, put an A, the letter A, because there's an A and a B for number 4. Number 4 should say, set the power source to 0. And A, for A is if the power source is a voltage source. If the power source is a voltage source, you set a voltage source to 0 by replacing it with a short circuit. If the power source is a voltage source, you set a voltage source to 0 by replacing it with a short circuit. If the power source is a voltage source, you set a voltage source to 0 by replacing it with a short circuit. There's a B, 4B. If the power source is a current source, you set a current source to 0 by replacing it with an open circuit. Step 4B. 4B. If the power source is a current source, you set a current source to 0 by replacing it with an open circuit. And then the last and final step, step 5, look into the output terminal and determine the resistance. Step 5, look into the output terminals and determine the resistance. Whatever value you get is the Thevenin resistance. Step 5, look into the output terminals and determine the resistance. Whatever resistance you get is the Thevenin resistance. Now, if you missed any steps, don't worry about it because we're going to go through it again. But this time, we're going to go through it on an actual circuit because I want you to see and draw a circuit diagram for every step I just gave you. So you should end up with 5 diagrams when you're done, probably 6 with the Thevenin circuit. So and we can just use this one. Let's just use this one. So let me show you an example of what I'm talking about. All right, so using the same circuit I just had, I'm going to draw it like we draw it in class. I'm not going to show it as part of a device. I'm just going to draw the circuit like this. All right. So over here on the left, I have my original circuit. Over there on the right, I got the Thevenin equivalent circuit. The Thevenin equivalent circuit is what the circuit looks like from the point of view of the load. This is the series. So what I want to do is I want to turn this circuit into that circuit using those steps I just gave you. So you want to get some paper down and you're going to write step number 1 again. Just write it again, but this time leave some space because I want you to draw what it looks like. So at the very top of the page, you draw this. Very top of the page, draw this, and you can type this is the original circuit. I'll give you, I'm gonna go slow, so I'll give you time to write. Go ahead and draw that at the top of your paper. And when you draw at the top of your paper, label this original circuit. This is the original circuit. Now what I'm going to do is I'm going to ask you to read me back each step. And what I want you to do on the paper is write that step down, and I'm going to do to the circuit what the step tells you to do. And I want you to have a picture of each step. So go ahead and make sure you got this circuit at the very top of your paper. Call this the original circuit. And below it, here are the steps to properly Feminizing a circuit. Now, somebody read step 1. What does step 1 say?
Remove load.
Remove the load. Remove the load. Don't take any shortcuts. Draw the circuit over. Remove the load. Here's what it looks like. You can't do what I'm going to do. I'm just going to do this. I can remove the load like that. You got to redraw it. So write step 1, remove the load, draw this picture. I'll give you plenty of time. Draw the picture with the load removed. Step 2, what does that say? Step 2.
Name the type.
Name the terminals. Name the terminal. What does that mean? Well, what you just label them. Call one terminal A, call the other terminal B. So I'm going to call this one right here terminal A. I'm going to call this terminal B. Now you might say to yourself, well, why do we got to do that? Why do we got to name the terminals? Well, if I give you a complex problem, often what you have to do when you Thevenize, and I'll show you an example of this, is you got to redraw the circuit. So if you name them, you can keep track of them. So for step 2, write down, name the terminal, and then redraw this picture again, even though it's the same as the one above it. But this time show an A and a B. So you know, if you look back at this a year from now, you'll know exactly how to do this. So draw this again. Under step 2, name the terminal and show the terminal's name. One is named A and the other is named B. Name the terminals. What's the next step?
Calculate the open terminal voltage.
Calculate the open terminal voltage. Well, what in the world is the open terminal voltage? Well, exactly what the words mean. Here are the terminals, and the terminals are open. Why are the terminals open? Well, the terminals are open because you removed the load. In other words, you have to calculate the voltage between terminal A and B with the load gone. That's what the open terminal voltage means. So calculate the open terminal voltage. And let me ask you a question. What I'm asking for is the voltage between terminal A and B. So here's my voltmeter. I got my digital multimeter, and I set it to volts. And I take one lead and connect it to terminal A, and I connect the other lead to terminal B. Whatever this is measuring now is the open terminal voltage. If I connect between terminal A and B, which resistor am I across? Am I measuring the voltage across resistor 1, or am I measuring the voltage across resistor 2 in this circuit?
I think resistor 2.
And you would think correctly. If you connect between here and here, you're across resistor 2. If you're not across 1, well, maybe this was across 1, but the bottom part, it can't get to it because the battery's in the way. Connecting from A to B is exactly like connecting across R2. What that means is if you find the voltage drop across R2, then you found the voltage between A and B. That's the open terminal voltage. So to find the open terminal voltage, all you got to do is figure out when you connect the voltmeter between the two terminals, ask yourself, which resistor am I measuring across? Whatever the voltage drop across that resistor is, that gives you VTH. Well, if I connect here, I'm across R2. So if I find the voltage drop across R2, that voltage drop will be my open terminal voltage, and that open terminal voltage is basically VTH. Okay, well, how do I calculate the voltage across R2? Now we're on this side again. We're looking this way. Looking this way, what kind of circuit is this?
Series circuit.
It's a series circuit. And looking this way, what is the input resistance of the circuit?
9.
9.
9. That 9, that input resistance, or we call it total resistance in the book, that's the resistance that the battery sees. And I didn't give this a voltage. Let's make it 9 volts. So all I'm asking you to do now to find the voltage drop across R2, basically just solve the circuit for V2. Well, everybody can solve a series circuit, right? It's easy. First step is to find the total resistance. It's 9. Then I got to use that resistance to find the current. Well, the current is just the total voltage over the total resistance that you found up here. And since I got 9 volts and I got 9 ohms, and the current's going to be 1 amp. So I got 1 amp flowing in this circuit. So if I want to figure out the voltage drop across R2, then I just use Ohm's law. It says V2 is is going to be the current through the resistor times the value of the resistor. The current is 1 amp. Resistance is 6 ohms. So my voltage is going to be 6 volts. Now I'm going to show you another way to do this. The voltage divider rule. We'll probably do it Ohm's law way a couple times, but anytime I'm doing this, I always like to use the voltage divider rule because it just saves a little bit of time. So if you want to do it the Ohm's law way, feel free to knock yourself out. But I don't want you to get confused about what I'm doing. I'm going to use something called the voltage divider rule. And here's what how the voltage divider rule works. It says that, let's say I got this resistor right here. And I want to know the voltage across that resistor. We'll call that voltage VR. If I want to know the voltage across that resistor, if I want to know VR, what I do is take that resistor, divide it by the total resistance. Take that fraction and multiply that by the total voltage. And whatever I get will be the voltage across the resistor that I want. So in other words, instead of going through these steps right here for Ohm's law, I could have said, all right, I want to know the voltage across this resistor. Put that in the numerator. Divide that by the total resistance. Well, you told me the total resistance, or the input resistance, is 9. Multiply that fraction by the total voltage. The total voltage is 9. And that'll give me the voltage across the resistor I'm talking about. That's 6 volts. See, doing it this way, I don't have to do step 2 of solving the series circuit. I never have to find the current. I go right to the answer. So this is a little quicker if you remember this formula right here, know how to use it. So again, if you want to use the Ohm's law way, knock yourself out. I'm going to do it voltage divider rule. Anytime I can do that, I always use the voltage divider rule. And by the way, abbreviate this VDR. So if you ever wonder what that means, voltage divider rule. Voltage divider rule. But whatever, we got 6. So what is that 6? That 6 is the Thevenin voltage. So now I know that this circuit right here has a Thevenin voltage of 6 volts. And we got half the problem done. All right, so what's the next step?
Set the power source to 0.
Set the power source to 0. Set the power source to 0. Okay. Well, what kind of power source do we have?
Voltage source.
We have a voltage source. There's only 2 kinds of power sources. There's voltage sources and there's current sources. And we really haven't talked a lot in here about current sources. A current source looks like this. If you've seen that symbol in the book, it's a current source. Usually when you get to like electronics or higher classes, sometimes you'll see the current source. I don't really do a lot with it. We'll do a little bit with it, but you'll get that in other classes. But if I have a current source, I set it to 0. I replace it with an open circuit, but that's not what I have. I have a voltage source. So how do I set a voltage source to 0?
With a closed circuit.
Replace it with a short circuit. And all that is a piece of wire. If I take a piece of wire and connect it from here to here, it shorts the battery out. It makes the battery voltage go away. It's gone. Disappears because I shorted it out. So I usually just show the short like this, and then I erase the battery. And so that's what the circuit looks like. If I short the battery out, set it to 0 with a short, then this is the new circuit I have. So go ahead and draw that circuit. I'll give you a minute to draw it, and then we'll look at that step again. Okay, so this is step 4. Step 4 says set your power source to 0. So you first identify your power source. If it's a voltage source, you set a voltage source from 0 by replacing it with a short circuit, a piece of wire. If it's a current source, you set a current source to 0 by taking it out of the circuit. You open it up. I checked, I had a voltage source, so I replaced the voltage source with a piece of wire with a short. That's called a short circuit. And what's the last step? The final step is what?
Look into output terminals and determine resistance.
Look into the output terminal and determine the resistance. See, before, when you found the total resistance, you were looking in this way. That's the resistance the battery sees. Now they're saying, let's figure out the resistance the load sees. The load is looking this way. You see, when I was looking this way, it was a series circuit, wasn't it? You told me the input resistance was 3 and 6, that's 9. But looking this way, what kind of circuit do I have?
Parallel circuit.
Parallel. Parallel. What do you mean parallel? Well, because looking this way, current only has one way it can go. We know in a series circuit, there's only one path for current. Looking this way, if the battery was back here, if I put that battery back, current can only go this way. There's one path for current, and whatever current flows through R1 has got to go through R2 to get back to the battery. There's one current, therefore they're in series. But if I put the battery over here, the current is going to come this way, some of it's going to go that way, and some of it will go that way. If it splits off, it can't be series. If it splits off, it's parallel. So looking this way, the battery sees this. The battery sees the total resistance as 3 ohms plus 6 ohms. It thinks it's hooked to a 9 ohm resistor. The battery doesn't know anything about a 3 ohm resistor. The battery knows nothing about a 6 ohm resistor. The battery thinks it's hooked to a 9 ohm resistor. The battery could really be hooked to 9 1 ohm resistors. It doesn't know anything about it. It only sees 9 ohms of opposition at its terminals. Likewise, the load. The load is looking this way, and it doesn't see R1 plus R2. It sees R1 in parallel with R2. Because looking this way, these two resistors are not in series. Looking this way, they're in parallel. I got this side and this side connected together, and then I got the other side connected together through that short circuit. They're in parallel. If you can't see that, all you got to do is take R1 and move it right there, and then you'll have a circuit where R1 is like that. You'll have a circuit where R2 is like that, and then you'll have terminal A, and then you'll have terminal B. They're in parallel. So what you got to do is figure out, what is that? What is 3 parallel 6? How much is that?
It's 2 ohms.
It's 2. It's 2. Well, how do you get that? Well, you could do this. You could say that 1 over REQ equals 1 over 3 plus 1 over 6. You do that, you will get 0.5, but that's not my resistance, that's my conductance. And if I want to do that, I got to take the reciprocal of that, and I get my REQ, which would be 2. Or you can use the product over the sum. I can take the product of R1 and R2 over the sum of R1 plus R2. You learn that in parallel. So I could have said, all right, I'm going to take 3 times 6 over the sum of 3 plus 6. On the top, I would get 18. On the bottom, I would get 9. And then I get 2. Either way, you get 2 ohms. So the resistance looking this way, from the point of view of the load, that's the total resistance, the equivalent resistance, the input resistance, whatever you want to call it. The resistance looking this way is 9 ohms. The battery sees 9 ohms. But the resistance looking this way, that's called the output resistance or the Thevenin resistance. The resistance looking this way, it sees these two in parallel. It sees a total resistance of 2 ohms. That's your Thevenin resistance. Whatever you get looking into the output terminal is RTH. So I know over here for RTH, I got 2 ohms. So here is my Thevenin equivalent circuit. I got a VTH of 6 volts. I got an RTH of 2 ohms. If I put the load looking this way, that load resistor knows nothing about a 3 and a 6 in parallel. It doesn't know anything about that. Looking this way, that load resistor thinks it's hooked to a voltage source of 6 volts. We know it's really 9. It sees 6 volts and 2 ohms of opposition. This is the circuit. This would be the equivalent output circuit. This is what the output of the circuit looks like. Now, if I get rid of this, and I put the battery back, and I put the load back, put that load back. If I hook the load up to this circuit, and then I took it off and hooked it up to this circuit, it's impossible, if that load can think, it's impossible for that load resistor to tell which circuit it's hooked to, because this circuit and this circuit are equivalent. Let's call this a Thevenin equivalent circuit, because from the point of view of the load, this is what it sees. Now, that's a lot. Anybody have any questions on what we talked about so far? Well, there's actually a second part to this. Because remember, one reason I said we do this, why do we Thevenize? Well, one reason is I take a complicated circuit and turn it into the simple circuit. And since these are equivalent circuits, it's easier for me to work with this, as you'll discover later on, than it is to work with this often. Not all the times, but often. So that's one reason why we Thevenize, because I get a simpler circuit. But there's a second reason that we Thevenize that I think is even either as important or maybe even more important than the first. And well, we've been talking for over an hour and 15 minutes. So I want to come back. Let's take a little break. And I want to talk about the second reason why we do this. Okay? So take a break. I don't know, maybe 5 minutes. Go do whatever you do when you're not on camera. Come back in about 5, 6, 7 minutes, and we will pick up class again and start. And then I'll show you the second reason why it's important to understand the Thevenin equivalent circuit, how to get it, and what it can do for us. Take a break, 5, 6 minutes, whatever you want to do here. Taylor.
Huh?
Hey guys, can you hear me?
Yes.
Yes, sir.
Sorry about that. I have a student here doing the lab. She comes in, I guess, to get caught up on labs and get ahead, and she was asking me some questions. But I'm going to try to share something with you. Hopefully, I don't get disconnected because I don't really share apps. But let me see if I can do this without getting disconnected. Just give me a second.
Hi, Rex Moore with the Motley Fool here, and I've got 5 free stock picks for you today.
I'm trying to, let's see. It's not what I want to do here. It's not letting me share the app that I want to share for some reason. It's not doing it. Share files. Let's see. Share application. Chrome tab. Okay. Yeah, okay. I think I can do this. Let's see. Can you guys see that? You see a hand?
I do not. Never mind, I do
There
now.
we go. I see a Newton's cradle.
Yeah, okay. Let me play it. Okay, can you hear me?
Yep.
Yep.
All right. So describe that. What did you guys observe? How did that work? What happened in the video?
False. Because of the false.
Okay. Well, what happened? What did he do?
What was that? The third law? What is it? The conservation of energy?
Conservation momentum.
Oh, yeah.
Okay. But you guys are using terms, those big terms, that's fine, but just what did you see in the video though? What did you observe? What did he do in the video? Let's say I have a bar right here, and I got a metal ball, and I got another metal ball. Let's say this is ball A, and that's ball B, okay? And what I want to do is, I want to give this some energy. And what I wanted to do is, the energy I give to A, I wanted to give it to B. I want ball A to give ball B the energy that I give it. So what I can do is I can pull it up like this. So ball A is up like this. And I'm giving it potential energy. I'm going to let it go. And then the potential energy is turning to kinetic energy. And it's going to strike ball B. And what I want to know from you is, what will happen if it was like this? What will happen if I have ball A like that, but ball B is like that? If I move ball A up to here and let it go, I want ball A to transfer its energy to ball B. And I want to transfer the maximum amount of energy from A to B. What will happen in a situation like this where ball A is way more massive than ball B? If I move ball A up here and let it go, describe what will happen.
If ball A was really, really more massive than B, it would cause it to bounce back and forth multiple times.
Okay, so if I pull ball A here, ball A is going to come here. It's going to strike ball B. Ball B is going to start going that way, and ball A is going to keep going. And then they'll end up going back and forth. Does that make sense? At any rate, if this is, as you say, way more massive than ball B, when ball A strikes ball B, they're both going to continue going that way. Would you agree to that?
Yes.
Okay, so that won't work. What if I reverse this? What if I made ball A like this, and I made ball B like this, and I pull ball A up here, and let it go? What will happen in that situation?
It'll maybe bounce off of it one or two times slowly.
Exactly. I bring ball A out. Ball A is going to strike ball B. Ball B might move over a little bit, but ball A is going to hit back and forth. It's not going to. If whatever energy I gave ball A, if ball A gave that energy to ball B, what should happen to A and what should happen to B? If ball A gave all the energy I gave to it to ball B, tell me what should happen to ball A and what should happen to ball B.
It shouldn't move.
Say it again. What shouldn't move?
The ball A wouldn't move if it hit
Okay.
B with all its energy.
Okay. So if ball A really did what I want, if ball A gave all of his energy to ball B, then what should happen is when I move ball A here, ball A should come down and strike ball B and stop. And then ball B should take off with the energy that ball A has, because it took all the energy from ball A. But it doesn't happen. When would that happen?
Sounds kind of like a ricochet effect.
Okay, well, what do I need to do with these masses to make that happen? I know if I make ball B bigger than ball A is going to bounce off of it back this way. If I reverse it, if I make ball B smaller than ball A, then ball A is going to continue going that way. How can I get ball A to stop when they hit ball B and ball B to take off with the energy that ball A had? What has to be true?
They have to be the same mass.
They have to be the same mass. If I have both of these the same mass, then in theory, when I move this back and I give it so much energy, if it strikes ball B dead center, when I give it energy, ball A will strike ball B, and ball B will move off and stop, and ball B will move off with the velocity and energy that ball A had. And that's the reason I showed you Newton's cradle. He kind of showed you that. You saw that when he picked up one ball, he hit the other ones, only one ball on the other side went up. When he picked up two balls and let it go, two balls on the other side went up. In other words, only when the masses match do I get maximum energy transfer from one to the other when there's a match. Well, this circuit works exactly the same way with power. Now remember what power is. All power is energy per unit time. And so if I want to get maximum energy from this circuit to that load, think of resistance like the electrical equivalent of mass. Mass is a type of resistance. It's called inertia in physics. So mass is a kind of resistance. So think of resistance as mass. And I want to get energy from one part of the circuit over to the other. The only way that can happen is if the masses, or that is, if that the resistors are the same. That's called maximum power transfer. Maximum power transfer. Let's look at it. I'm going to share that document with you that I had before. So if you look at this document, we've already talked about Feminist Theorem. We described that. If you go down on the page, you'll see there's another one. Read this to yourself, number 2. Read that to yourself. Maximum power transfer theorem. It says a load will receive maximum power from a linear bilateral DC network when the total resistive value is exactly equal to the Thevenin resistance of the network as seen by the load. A load will receive maximum power from a linear bilateral DC network when its total resistive value is exactly equal to the Thevenin resistance of the network as seen by the load. In other words, guys, if whatever this device is that we got this circuit from, whatever the device is, I can hook up as a load any value resistor I want. But if I want maximum power to go from the voltage source to the load, there's only one resistor I can hook up, and it's a resistor where RL equals RTH. Just like in Newton's cradle, if I want the energy from one ball to be transferred to another ball, the maximum amount of energy is going to happen. It's going to transfer when the masses are equal. Well, if I want my original power source to transfer maximum power to the load, then that's only going to happen when the Thevenin resistance and the load resistance match each other. So if I want maximum power to be transferred from that 9-volt battery to this load, and that load resistor got to be 2 ohms. You guys probably don't do this nowadays, but anybody ever install a stereo in their car? Used to be something we did back in the day quite often, but now the stereos in cars, number one, are pretty good, so you don't have to put in the aftermarket stereo. And number two, the newer cars nowadays are way harder to work with. But I used to install amplifiers and stereos in cars and alarms and all of that a long time ago. And if you look at an audio amplifier for a car, there's a left channel and there's a right channel. And then you got these terminals there where you can hook up speakers. I can hook up a speaker on the left channel, and I can hook up a speaker on the right channel. Anybody know why there's a left and right channel in audio? Why is there a left and a right channel?
For stereo.
For stereo. We hear in stereo. If you want to hear in mono, just cover up one of your ears and hear how things sound. We hear in stereo. And so when we hear sounds, it comes into both ears, but it doesn't come directly from the source to our ears. Some of the sound does, but some reflects off of the wall and the surroundings. That's called reverb. And so if you want to hear things exactly how the sound is produced, you want to hear in stereo, you got to have two mediums, 2 sides, the left and the right. So when they record in stereo, they literally have 2 microphones like this, and in place of your ears, that's a left channel and a right channel, or a left track and a right. It's for stereo. And when I install these amplifiers, let's say the amplifier was 100 watts per channel. Well, I always noticed that there was an ohmic value on the output of the amplifier. For the left channel, it was 4 ohms, and for the right channel, it was 4 ohms. I always noticed that. And I knew what that meant. It meant that I got to go get a speaker, and the speaker needs to be 4 ohms. If they had a 2 ohm there, I need a 2 ohm speaker there. And I always thought, well, they were telling me with this number stamped on the amplifier, they were telling me what ohmic value speaker I needed. And that's kind of right, but it wasn't really right. Here's what they were really saying. What they're saying is, if you took the speaker off of here, and you can look back into the output of that amplifier, you can see in the output and look at the resistance. Now remember, when you look into the input of something, that resistance is called the input resistance. It's called the total resistance. It's called the equivalent resistance. That's the resistance that the power source sees. But when you look at the output, that's the resistance that the load sees. That's called the output resistance or the Thevenin resistance. So by putting that little sticker there and saying 4 ohms, what they were really saying was the resistance looking into the output of an amplifier, this resistance, is 4 ohms. Now, you can hook up whatever ohmic value speaker you want. You can hook up a 20 ohm, you can hook up a 100 ohm, you can hook up a 1 ohm. You can hook up any ohmic value you want. But if you want maximum power, you want all of this 100 watts, or most of this 100 watts, to go from the amplifier to the speaker, and that speaker has to have what ohmic value?
4.
It's got to be 4, just like Newton's cradle. So if this was a speaker, if this was the amplifier, and the load was the speaker, I got to make that 4 ohm. If it was any number other than 4, I wouldn't get anywhere near 100 watts. Maximum power transfer theorem. Now don't confuse this. I'm not saying that these two have to match. They only have to match if the purpose of your circuit is to get maximum power from the power source to the load. If that's not your concern, don't worry about this. But if that's your concern, that only happens when this is true. And with an amplifier, that's what you want. Matter of fact, in a lot of situations, you want maximum power to be transferred from the voltage source to whatever the load is. That, to me, is one of the most important reasons to Theavenize. Questions over that? Now, this is the part of the course where students start to have a little bit of trouble. So I want to do some practice now. I want to practice Theavenizing. So what you'll need for this next part, guys, is you need a couple sheets of clean paper, blank paper. You'll need your calculator and that list I gave you on the steps to properly Theavenize. And what I'm going to do is share a document with you with some example problems on it. And each problem is designed to teach you something. So it's important that you look at each problem. Now, the very first problem, this one, is just kind of a warm-up to give you a chance to practice what I went over earlier. This is just kind of a warm-up, see if you got the steps down. But after that, each problem is designed to teach you something. So I wanted to make sure you're clear on what the takeaway is for each problem. So get a sheet of paper out, and on that paper, draw this first circuit, figure 1. And then have that step, those steps that we just went over in the last hour, have that right next to you. And what I want you to do is, using those steps, Theavenize the circuit. And then give me all these values over here for your circuit. Okay, so draw this on a sheet of paper and find all these values and draw the Thevenin equivalent circuit. And I'll give you a while to do it, and then we'll compare notes, see what you got, see what I got. So go ahead and work with that, and I'll come back on camera in just a little while. Okay, guys, I'm gonna give you about 2 more minutes on this circuit, and then I want to talk about it. All right, let's take a look at this. Well, one of the things you want to find is the input resistance. The input resistance is the resistance from the point of view of the battery. The input resistance is the resistance looking this way, looking in that way, into the circuit. What is the input resistance of this circuit?
Would it be 16 ohms?
It is 16 ohms.
Awesome.
Yeah, the input resistance is 16. Good job. If you're wondering why, well, remember, this is the device. This is the thing that the device is controlling. This is not part of the circuitry. The load is not part of the device. So what I got to do is disconnect the load, take the cell phone off the charger. If I want to know the resistance of the charger, I don't have the cell phone hooked to it. Then I will get the resistance of the charger and the cell phone. That's not what I want. I want just the charger, so I remove the cell phone. So looking at it this way, in the circuit that the battery thinks it's hooked up to is a series circuit, and in series, R1 plus R2, in this case, is 16. So my input resistance is 16 ohms. Now what I want to do is Thevenize the circuit. So if I Thevenize this circuit, let me ask you, did anybody get a value of VTH? What did you get?
84.
8.
I said 42.8 volts.
You got 8 volts. You got 42.8 volts. Anybody get something different? What about RTH?
RTH, I got 3 ohms.
3 ohms. Anybody get something different? Everybody got 3, or somebody get something different?
Yeah, I got 3.
Okay, well, let's check. So step 1, remove the load. Step 2, name the terminals. Step 3, measure the open terminal voltage between A and B. If I connect my battery here, if I connect my voltmeter here, which resistor am I across?
You would cross where it says 4 ohms.
I'm across, yeah, that's R2. So if I find the voltage drop across the 4 ohm, that's my VTH. Now you can use Ohm's law if you want to. If that's what you did, fine. I'm going to use voltage divider rule. voltage divider rule says take the resistor I want to know the voltage across, is 4. Divide that by the total resistance. You told me that was 16. Multiply that fraction by the total voltage, it's 32. And that's going to give me VTH. So if I divide out this, divides out this 2, and 4 times 2 is 8 volts. So whoever got this, your VTH is 8 volts. If you got something other than 8, try to figure out what you did and understand why it's 8. Questions over VTH? Well, if there's no questions over VTH, now we got to find RTH. So to find RTH, I got to set the power source to 0. That's a voltage source. If it was a current source, I would set it to 0 by removing it. That is, opening up the circuit. This case is a voltage source. So what I do, I take it out of the circuit and I replace it with the short circuit. Now, R1 and R2 are already tied together right here and right here through that wire. As soon as I put that short circuit in there, it ties the other side of R1 and R2 together through that wire so that RTH is going to equal the parallel combination of R1 and R2. It's those two in parallel. So what I got to do is I got to take 12 ohms in parallel with 4 ohms. If you do product over the sum, or you do 1 over R rule, you'll find out that that's 3 ohms. So whoever got this, you're correct. We draw this Thevenin circuit, VTH. You said that was 8 volts. RTH. You said that was 3 ohms. So here's my Thevenin equivalent circuit. The load doesn't know anything about this circuit. The load sees this circuit. And then they say, all right, well, if I want maximum power to be transferred from this 32-volt battery over to the load, what value should I make the load? Well, that low resistor value has to match the Thevenin resistance. So this would be 3 ohms. So I put the load back over here, and I make it 3 ohms, and it's going to get maximum power from the battery over to that thing right there. That's a speaker, maximum power. That's a light bulb, maximum power. That's a cell phone, and this is your charger. You want maximum power charging that phone, they got to match. So if somebody did really well, some of you got both values of VTH and RTH. If you didn't get them, that's okay. That's fine. But make sure you understand what you did wrong. And if you can't understand what you didn't get right, then you want to make sure you ask. So any questions on that first problem? That was just one to give you some practice doing Thevenin. The next one, we're going to teach you something new. So anybody have any problems on, any questions on the problem we just went over? All right, well, I'm going to share that document, and I want to now move to figure 2. So look at figure 2, and let's do the same thing with figure 2. Give me all those values, and again, I'm going to give you guys a little bit of time to work on it, and we will talk about it shortly here. So go ahead and see what you can do with figure 2. You guys, I'm gonna give you about 2 more minutes to work on this problem, and then I'm gonna give you, talk about it. All right, let's take a look at this problem. What did you got? Anybody get a value for Rn? What did you get for Rn?
6 volts.
6. Anybody get something else for Rn? One person got 6, and I guess everybody else didn't get anything because nobody said anything. What about RTH? What you get for RTH?
I got 3 ohms.
3 ohms. Anybody get something different? And what did you get?
I got the same one.
Okay, anybody else get something different than 3? What about VTH?
I had 20.
Okay, 20. All right. Anybody else?
I got 50.
50.
54.
50. Got 20, 50. Anybody else? All right, let's look at it. So Rn is the resistance that the battery sees. So we look at it in this way. But you got to disconnect the load. So if I take the load off, and you say, all right, well, how much resistance is this battery facing? What's it saying? Now, you got to remember, how does the battery know something's out there? What is it sending out there to feel the resistance? Well, the answer is it's sending current out there. It's pushing current through the circuit. So it's only going to feel the back push or the resistance or the opposition from whatever it's pushing current through. If it doesn't push current through it, then it doesn't have a resistance. So if you think about it, what path is current flowing through in this circuit? Well, current is coming through here, so this is going to have to push through R1. Will it have to push through R3? Well, the answer is no, because it's open over here. When you take the load off, no current can come this way. So the battery has to push through R1 and push through R3. It just sees these two resistors and they're in series. It doesn't know anything about R3. So it sees 3 ohms of opposition and another 3 ohms of opposition. 6. It sees an input resistance or total resistance or equivalent resistance, whatever you want to call it. The resistance based on the battery, resistance the battery thinks it's hooked to, the total resistance of the circuit is 6 ohms. All right? Well, let's Thevenize it. So when I Thevenize it, I remove the load. Mark the terminals. Set my power source to 0. That's the voltage source. So to set that to 0, I remove the voltage source and I replace the voltage source with a piece of wire. Now R1 and R2 are already tied together right here and right here. When I put that piece of wire here, that's going to connect the other side of R1 and R2, making those two resistors be in parallel. But we're not there yet. I want to find VTH. So VTH says, all right, if I take my voltmeter, oh, why did I short this out? I jumped ahead of myself. I can't find VTH without a battery. So let me back up, put this back. I guess I'm getting tired. When I start making a lot of mistakes, I'm tired. So I'm getting there. So we got to first put my voltmeter here. And when I put my voltmeter here, I said, all right, put my voltmeter here. Which resistor am I measuring across? Am I across R1? Am I across R2? Am I across R3? Am I across some combination of maybe 2 resistors? Which is it? Well, this is the second thing, or the first thing I want you to learn. This resistor right here doesn't have any current through it. A resistor with no current through it is not dropping any voltage. So if a resistor that's not dropping the voltage, you might as well, you could do this. If it's not dropping any voltage, you can take it out of the circuit and replace it with a piece of wire. A resistor with no current going through it acts just like a piece of wire. So even though that resistor is hanging there, when you put the voltmeter across it, since there's no current going through it, because the voltmeter doesn't draw current, there's no current going through the voltmeter. So by putting this here, you're not closing that path off. There's no current flowing through R3, so like R3 is not there. It's just like a piece of wire. You could take and put the voltmeter here, and you can move it over there. It'll have the same exact voltage because it's like R3. It's not there. It's not dropping any voltage. So whatever the voltage is across R2. That's going to be my voltage across A and B. You can ignore R3 if it's just hanging there. A resistor just hanging there with no current going through it, You can mentally replace that with a piece of wire, which means connecting up here, it's like connecting here. So if I can find the voltage drop across R2, I got it. And I don't even have to use voltage divider rule for that because I got this series circuit in here. I got 3 ohms and 3 ohms, so each one's going to drop the same amount of voltage. So since I got 100 volts, each one's going to get half. I want to have 50 volts across R2. Therefore, my open terminal voltage is 50 volts. So whoever got this, you're 100% correct. All right, now I'm going to put this resistor back in there. And now I'm going to find my Thevenin resistance. And that's what I'm going to replace that with the short circuit. And as I was saying, when I do that, and I put the wire here, it puts these two in parallel. So if I'm looking in here, here's my eyeball, I'm looking in here. What I see is R3. That's the first thing I see. And after I look through R3, on the other side of R3, I see R1 in parallel with R2. That's what I see for RTH. So look at this equation and look at what you see on the board and make sure you can see the relationship between the two. The resistance looking through A is going to be R3 plus the parallel combination of R1 and R2. Now I got 3 ohms in parallel with 3 ohms. 3 in parallel with 3, if they're the same, you just divide by the number of resistors you have. So I can take one resistor and divide by the number of resistors I have, and I get my answer. So 3 in parallel with 3 is 1.5, half of 3. 3 over 2 resistors is 1.5. So this part is 1.5, and this is 1.5. I add them together, I get 3 ohms. So my RTH is 3, and if I want maximum power transferred to this load right here, and that load has got to be 3 ohms. Only if you want maximum power. If you don't care about maximum power transfer, you can make that whatever you want. If you want maximum power to go from the 100 volt source to whatever this thing is right here, you gotta make this thing, the ohmic value for that 3 ohms. It's gotta match the Thevenin resistance. Questions over that problem? All right, well, if you didn't get that one, if you made some mistakes, try to see where your error lies, and you got a second chance at it because this next problem is similar. See what you can do with figure 3, this one. We'll talk about it. As to give you about 2 more minutes on this problem, and then we'll talk about it. 2 minutes. All right, let's take a look at the problem. Can somebody tell me what the input resistance is?
The input resistance, I got 12 ohms.
12 ohm.
Rn 12. Anybody else get something different?
I got 12, but I'm a little bit unclear about what input resistance is.
Okay,
So
that's fair. We'll talk about it. What about RTA?
I got 5 ohms.
RTH, I got 5
5
ohms.
Anybody get something different than 5? What about VTH?
I
9
got
volt.
9 volts.
Okay.
Same.
Anybody get something different than 9? All right, well, let's talk about it. Let's get the input resistance. So if I want the input resistance, I first got to take the load off because it's not part of the actual circuit. It's what's being powered or controlled by the circuit. And then I'm looking this way to see what the battery sees. The battery can only see what it can push current through. So just ask yourself, which resistors is current going through and how are they connected? Well, clearly current's going to come out of the battery and go through R1. So we're going to feel 3 ohms of opposition for R1. No current is going to go that way because where will it go? It can't go anywhere. It's an open circuit. So current is going to go through R1. It's going to go through R2 and then come back to the source. So it's going to see these 2 resistors in series. It will not see R3. The battery does not see R4. It sees 12 ohms of opposition. So whoever said the input resistance is 12, you are correct. Questions over why it's 12? Anybody got questions? The key there is to just follow the path of current. If current doesn't go through a resistor, then when you're trying to find the input resistance, it's not there. And then you got to see how the resistors are connected. In this case, they're in series, so you're going to add them up. If I had another one here that was in parallel, then that current would split off, and I would have to do a parallel calculation. But follow the path of current. So, a lot of you got 12, then that's great. You got the right answer. Now we feminize. So now looking this way into the circuit. What does the load see in terms of R and V? Well, I remove the load. I name my terminals. Here's terminal A. Here's terminal B. And I connect my voltmeter up between the two. The question is, when I connect my voltmeter up, which resistor am I across? You might think, well, I'm across R3, and you would be wrong. You might think I'm across R4. You would also be wrong, because those resistors don't have a current going through them. A resistor can only drop voltage when current is going through it. I mean, that's what the equation says. The equation says that if I have a resistor, the equation says if I have a resistor and I send a current through the resistor, I get a voltage across that resistor. If you make this current 0, then that voltage drop is 0. If it's not dropping voltage, it's like a piece of wire. So what you can do, imagine this as a piece of wire, and imagine this as a piece of wire, only when you're trying to find VTH, not RTH. This is only true for VTH. So if these were wires connecting here, is exactly like connecting across R2. So if you find the voltage drop across R2, you found VTH. And again, I'm going to use the voltage divider rule. Voltage divider rule says take the resistor I want to know the voltage across, the 9 ohm, divide that by the input resistance. The input resistance, looking this way, you told me that was 3 plus 9. You told me it was 12. Take that fraction, multiply by the total voltage, and that'll give me VTH. Well, you can see the math is nice to us. These are going to cancel out, so I'm going to get 9 volts for VTH. So somebody got 9 volts. So got 9 volts, you're good to go. RTH. Well, now I got to put these back, because these come into play for RTH. And this is where I set my voltage source to 0. I do that by replacing it with the short circuit. So when I erase, when I take this out and replace it with the short, as soon as I connect this wire to this wire with this, it puts R1 and R2 in parallel, because they're already tied together right here and right here. So shorting out that battery makes these two in parallel. And you're looking down through there. If you're looking down through there, the first thing you see is R3. If you're looking at terminal A, the first thing you're going to see is R3. And then after R3, you're going to see those two, R1 and R1 and R2, but they're in parallel. So you're going to see these two in parallel, R1 and R2. And then after that, after these two parallel, you're going to see R1, R4. You see R4 like that, and then you got B. So looking in there, you got R3 plus this, which is R1 in parallel with R2, plus what's left is R4. That'll give you RTH. Put my values in. R3 is 0.5. I got 9 parallel 3. How much is that? 9 parallel 3. Anybody?
9 parallel 3 was 2.25.
2.25. R4 is another 2.25. So that'll give me, if I add, that'll give me 5. So RTH is 5. And so my Thevenin circuit, I got 5 ohms for RTH. And I forgot, what was our VTH? Was it 9?
VTH was 9 volts.
All right, so here's my Thevenin voltage, my Thevenin circuit. And if I want maximum power to be transferred from that 12 volt battery to the load, I got to make the load equal 5 ohms. If I don't care about maximum power, load can be anything you want. So if you got that one right, that was kind of a next step up from the figure before it. You should feel pretty good about yourself. Questions or comments on anything we did so far? Okay, I got one more problem. Now this next one is kind of a tough one. So put your thinking hats on and just use logic and what you know about circuits and see if you can come up with these answers. Sometimes it helps to redraw the circuit. I don't know if you will need to, but we're doing figure 4. So see what you can do with that. We'll talk about it, and then after we get done with this, I think we'll call it a night because I won't be able to do much more here. I'm trying to fall asleep on you guys. So see what you can do with it. We'll talk about it shortly. Okay, guys, I'm gonna give you about 3 more minutes on this one. Then I want to talk about it. 3 minutes. All right. Let's see what we got. How about Rn? Anybody get a value for that?
2 ohm.
2 ohms. Anybody get something different?
No, sir.
Okay. What about RTH?
I have 1.5 ohms.
1.5. Anybody else?
1 ohm.
1 ohm. Anybody else? About VTH.
I got 25 volts.
25 volts. Anybody get something different? We got, people tend to agree on Rn as 2. You got 2 possible answers for RTH. I got 25 volts for VTH, and then some of you did the answer, so you probably got something, you just don't want to share it. Let's look at it. So my input resistance, how much does the battery see? So the battery's looking up this way. Now remember, the way the battery tells something is hooked up is by sending current out. So I want to see how much resistance it sees looking up that way, but I don't want this to be in that. I got to take this away because I don't want this to be added to it. That's not part of the device. It's not part of the circuit. So you send current out and watch what happens to the current, and that tells you which resistors are in the site of the battery. And then you got to determine if those resistors are in series or parallel to see how much resistance the battery feels. So the battery is going to send current up like this. And at this point right here, some of the current is going to go that way, and some of the current is going to go that way. So the current that goes this way has to push through 4 ohms. So it's got to push through 4 ohms. And the current that goes this way has got to first push through 2, and then it's got to push to another 2 to come back to the battery. So you can see that these 2 are in series. So it's got to push through 4 this way, it's got to push through 4 that way. So it's got to push through 4 on the other side. Now, how are these 4 ohms connected? Well, this branch and this branch are in parallel. If you can't see it, then if I make this circuit taller, like if I stretched it out, if I redraw it, I can draw this one like this. I can have my battery right here. If I stretch this up so it's straight, then what I would have over here, I have R2 here, and R3 would be here, and I would have this terminal here, and this terminal there. So I got this branch in parallel with this branch. There's 4 ohms in this branch, and these 2 add together. There's 4 ohms in that branch, and those 2 4s are in parallel. So my R in is 4 in parallel with 4, which is 2 ohms. My input resistance is 2 ohms. So I know at least one person got this, maybe more. People tended to agree on that. If you got 2 ohms, you would be correct. If you didn't get 2 ohms, try to see why you were not correct and make sure you understand why you were incorrect. The answer is 2 ohms. Now, to Thevenize it, we remove the load, we mark the terminals, and then I gotta ask myself, all right, if I put my voltmeter between the terminals, which resistor am I across? And I can clearly see on this one that I will be across R3. So whatever the voltage drop across R3 is, would be my Thevenin voltage. And you can really see it over here. You can see that that battery is 50 volts. This battery is 50 volts. That 50 volts extends from there to there. So R1 gets 50, and these 2 over here get 50, a total of 50. But since these 2 are the same, this will get half and this will get half of the 50. This 4 ohm over here drops the whole 50. But over here, R2 and R3 are both 2 ohms, so they're going to get half the 50. This will get 25, and that'll get 25. Kirchhoff's voltage law teaches us that this plus this has got to add up to the 50. So if I connect between these two terminals, I'm connected across R3. R3 is dropping 25 volts. Therefore, VTH is 25 volts. Anybody have any questions over VTH? So again, if you got that, then good job. If you didn't, just try to see why you didn't get it and try to understand it. It often helps to redraw the circuit, and that's the idea of labeling these so you can keep track of them when you redraw it. This makes it easy to keep track of. All right, now, remember I said that each circuit is designed to teach you something? Well, you learned that if I have a resistor just hanging out there with no current going through it, then it can't drop a voltage. So when I find VTH, I ignore it if it's just hanging there with no current going through it. Well, this circuit teaches you one more concept to watch out for when you Thevenize it. So let's look at that. So now I want to find RTH, and RTH is what the load sees. So now I'm looking in this way. So what I got to do is I got to set my power source to 0. It's a voltage source, so I'm going to set it to 0. I replace it with the short circuit. Now, when I put the short right here, when I put the short circuit here and here, when I do that, basically this resistor is connected to itself. It's like taking a resistor, and I don't know if you can see, I got a resistor here. It's like taking a resistor and bending the leads and connecting it to itself. So if I take a resistor and I connect the leads to itself, when I try to measure the resistance, it's going to measure 0 because none of the current goes through the resistor, it just goes through the wire. In other words, we say that the resistor is shorted out. So let me show you another way. Let's say I got a resistor. I don't know if you can see the screen. Let me make it. Let's say I got a resistor. Let's say it's 100 ohms. So I got my ohm meter over here. I got my leads hooked up to the resistor. And it's measuring 100 ohms. Well, while my ohm meter is hooked up, if somebody comes in here and takes a piece of wire and connects it like that, then the reading is going to change from 100 to 0 because that's a short. You shorted out the resistor. The way the ohm meter works is the ohm meter actually sends out a current. And if I don't have this short here, the ohm meter has a battery and it'll send out a current and go through that 100 ohm resistor, and that's how it knows how much its resistance is out there. The current has to push through it. But if I put a short, well, the short circuit is like a bypass. And when that ohm meter sends the current out, current takes the path of least resistance. Well, the short doesn't have any resistance, so current's going to bypass the resistor and go back to the ohm meter. It's going to think there's nothing out there. So anytime you have a resistor connected to itself through a wire, then the resistor shorted out, it's like it's not there. If you look carefully at this, this resistor is connected to itself through this part right here. This part that I'm shading in connects the top of R1 to the bottom of R1, so it's shorted out. It's not in the circuit. You might as well just erase it and put a wire there. The actual circuit, looking this way, the actual circuit that you see, if I short this out, it's like this resistor's not there. I short that out. It's like, and this is the circuit. You see, you're looking in this way. If you're looking in that way, you see current can come in that way, and current can come in that way. That means these two have to be in parallel. So looking in that way, you don't see R4, you see R2 and R3 in parallel. You take 2 ohms in parallel with 2 ohms, you get 1 ohm. So RTH is 1 ohm. Somebody figured that out. It's 1 ohm. So my Thevenin circuit, VTH 25 volts, RTH 1 ohm. And if I want maximum power to be transferred from that 50-volt battery to whatever my load is, I gotta make that load equal to 1 ohm. That's a pretty good problem. So the takeaway on this circuit, what I want you to remember is, if that battery has anything in parallel with it, in this case, the battery had R1 in parallel with it. If it has something in parallel with it, when I short it out, it's going to short that thing out. Okay, so that battery shorts it out. Current does this. If current was coming in here, current has to go through this resistor. And current can split to go through this resistor. But over here, it's going to go right through the short to get back. So the path of current, one path is through here, and the other path is through here. None of them will go through there because current takes the path of each resistance. So that one you got to probably redraw and think about, maybe rewatch the video. But let me show you one more quick thing. I know it's late. Let me show you one thing.
So just so I make sure I'm understanding this, R1 in this case didn't have an effect on VTH nor RTH.
No.
For both of those, you could ignore it.
In this case, yes. So what if I gave you this? Let me make it neater. Let's just make these all 1 ohm. That's 1, that's 1, that's 1, that's 1, that's 1. And this is resistor A, B, C, D, E. And I want to know which resistors are in the circuit and which are not in the circuit. When I want to find, I'm looking this way. I'm going to get this going. I'm looking in this way. I'm looking for RTH. I want to know which resistors are in the circuit and which are not in the circuit. So I'm going to give you about 1 minute to decide which are in the circuit and which are not in the circuit when I set this up to find RTH. All right, so if I'm looking this way, which resistors can I ignore?
A.
A, okay. Anybody else?
A and B.
A and B, anybody else? Okay, let me show you how you would tell. I gotta short this out. So we'll take this off. I'm gonna short it out. Okay, so I'm gonna draw I'm gonna shade in this short. So when I connect that short here, I got this wire right here. Notice I don't have another resistor. Come right here. I go over to here. Let me shade this in. You see how resistor 1, the orange touches both sides of resistor 1? It's shorted out. It's not there. You see how B, the orange touches both sides of B? It's shorted out. Anytime a resistor is touched both sides by a short, it's not in the circuit anymore. That's not the case over here. C touches this side of it, but this side is okay. And down here, I can extend this all the way out to here by 1. D touches one side of it, but this side doesn't touch. So these two are actually still in the circuit. Matter of fact, the equivalent circuit, if I redraw it, here's the equivalent circuit. I got E. I got D. I got C. And then everything else on this side is shorted out by that wire, and then my lead comes out like that. So by doing that, this is actually this right here. So these two are in parallel, and that's in series. And I can see that because when I shade this in, any resistor that has the same color on the top and the bottom is shorted out. So that's a good way to do that, guys. Now, questions or comments? I want to give you a homework. I want to see if you have any questions or comments before I give you the homework. All right, well, here's what I want you to do for homework. Either in your book, well, I probably want to do your book. So you got to have a copy of the book. Guys, if somebody doesn't have a copy of the book, then let me know and I'll send you the link to an electronic copy. But what I want you to do for homework is go to look up Thevenin in your book. Excuse me. I don't know what chapter it's in. It should be under methods of analysis or something like that. Or it might be under circuit theorem. It's one of those chapters. Look it up in the back of the book. I want you to get 3 of the problems out of the back of the book. Work them out on a piece of paper. Take a picture of it with your cell phone and send the picture to me. Between now and next class. Now, don't do anything in the chapter. I want something that's one of the problems in the back of the book. If you're smart, if you do a odd number problem, the answers are in the back of the book for the odd problems. That way you can check to see if you're doing it right. You can do like, I'm not going to tell you which ones to do. I just want you to practice this some more before next class. So pick about 3 problems, take a picture of them, and make sure that you get a response from me so that you know at some point, not as soon as you send it, but within a day or so after you send it, you should get a response from me saying that I got your work. And I'll go ahead and grade you and give you a homework grade of 100 points if you get everything right. So let's make it 2 problems. Let's just do 2 because that's a lot of grading for me. So get 2 problems. Don't get anything like super, super easy. You might do one that's kind of a medium one and maybe one a hard one. I'm not going to, it's up to you, but you want to try to learn something. That's my point. Anybody have any questions or comments?
So
Okay,
the
so-
homework will be sent to the by using message or email.
Say it again. Say it again.
So how can I send to the photos of the homework?
Yeah, you're gonna send it. Text me this number.
Okay.
Well, yeah, because some people might not have a. I know you got an app you can scan. What you can just send me a text.
Yeah.
So you can text it to where you text the attendance.
Okay.
Or if you guys are, if you're able to scan, I can make it a link that you can upload to Blackboard. Would you guys prefer that? What do you want me to do? Is that better for you? If I make it a link, you can. I don't know if you can scan this.
I can do whatever you need me to do, really. With like scanning it, it actually print it out. It's usually like some of them they want you to pay, but you can just send it to yourself on an app like Facebook. Like send it to your own Facebook, right? Download it, email it to someone, or really something like that. Like send it to your own email, download it on your computer, and then upload it from the computer.
Well, just go ahead and snap the picture with your cell phone. Just make sure you get everything in the frame so I can see it, okay? And do about 2 problems. If you want to do more, that's fine. But do at least 2 because I want to know you're practicing this before next class. So just send it to that number, and that way we don't have to worry about any. I don't want you to have to pay for anything, and it's just I don't want you to have to go through a lot of trouble. But just give me a couple days and make sure you got a response from me to say, and I'll just send you your grade right away. I'll just say, hey, if you don't get a grade from me like a couple days, then send me another. What do you call it, poke me? Send me another text. Say, hey, you need to grade my work, and I'll get to it. And I'll get it done for you. So, okay. Anybody have any questions, problems, concerns? All right, guys. I'm getting really tired, so I'm gonna have to get out of here, and I still gotta go feed my 6 dogs. So, if you have anything come up, send me a text sometime tomorrow. I'll be happy to take care of it. And also, we need to think about another exam. I don't know, but watch your Blackboard because I know the day class is going to take an exam next week, but you're kind of behind them a little bit. We lost a day when I had you come in for lab, or something happened. I lost a day, so I'm not sure. I don't think I want to give it to you next week. But see, we're running out of time, and we still got 3 more exams. Now, one of the exams is a take-home, so I'm not too much worried about that. So I need to see how we're going to work this out. But watch your Blackboard in case I decide to give you something to do at home for exam. And I'll send out an announcement if something like that happens. All right, guys, I'll see you in about a week. Again, just keep an eye on Blackboard in case I send you a message, and I'll talk to you later.